This video is applications of definite integral. We will be looking at volume as an integral of cross-sectional area, or volumes of solids whose cross-section is a known shape. Semicircle, square, rectangle, parabola, all those. Okay, so we know how to find the volume of a solid like a pyramid or a cube using geometry. What if our solid looks something like this? As you can see that it's not a shape made up of planes. There's curved surfaces. So the techniques we know so far of finding the volume would not work. We can still find the volume of such solid as long as we know how to find area of one of its cross section. That's what this section is all about. So here's an example, a solid whose cross sections are, the base is a circle and the cross sections are squares. Another example, the base is a parabola and the cross sections are semicircles. Another example, so this section we are focused on finding the areas of volumes of such solids whose cross sections area we know how to find. Let AY be the area of horizontal cross section sitting at the height y of the solid body extending from y equals A to y equals B. We will find the volume of solid by integrating volumes of small cross sections. So our goal would be to find the volume of the small one slice. Our goal would be to find the volume of one slice and then integrate over the range of x values or the y values. Okay, so the volume of solid is going to equal area of cross section times a dy or dx. Okay, we will use dx, or the width of cross sections will be delta x if cross sections are perpendicular to x-axis. So if cross sections are perpendicular to x-axis, we'll use dx. If cross sections are perpendicular to y-axis, we will use dy. F of x will be used if cross sections are perpendicular to x-axis, f of x will be used and a and b will be the limits x values. Okay. We'll be using dy if cross sections are perpendicular to y-axis, and a and b will be the y values. Limits of integration, f of y will be used. Okay, so keep in mind, if your cross sections are perpendicular to x-axis, then their width is in terms of x. Our integral will be in terms of x. Everything has to be in terms of x. And if your cross sections are perpendicular to y-axis, the width of each cross section will be delta y, and the limits would be the y values, and we want the whole integral in terms of y. Okay, so we're going to start with an easier example. Find the volume of a solid with circular base of radius 2 and the cross sections are squares perpendicular to x-axis. So only thing that you need to spend some time on is to find the area of one cross section. Once you have area of one cross section, from there things will get easier. Okay, so here's the one cross section whose area I am looking at or I want to find out. Once you have area of one cross section, we can find the volume of one cross section. From there, we can find the volume of the solid. Now here, cross sections are perpendicular to x-axis. That means width of each slice is delta x. Width of each slice will be delta x. Okay, imagine this is the width of each slice and that's delta x. Okay, so we want to find out area of one cross section. Area of one cross section. Good thing the cross sections are squares in this case. Finding the area of a square is not too much work, but let's think about how much is the side of the square. Because to find the area of square, we need the side of the square. So how can I find side of the square? The pink side that I just colored for the square. If you look at it carefully, the bottom is a solid whose it's a circular base equation of circle with the radius 2 will be x squared plus y squared equals 2 squared, which is x squared plus y squared equals 4. The radius of each circle, or you can say the side of the square, is each y value. Half of the side of the square is each y value. So this pink side is actually y value plus y value. Maybe it's easier if I draw them on the side here. So this is where, not a good picture. Let me try one more time. Trying to show you a 3D shape in 2 dimensions. So let's see. Now that doesn't look good either. Anyways, so this, okay, no, I'm not happy with it. Anyways, so let's go back at the shape we had earlier. I am trying to find out this little piece and this little piece, and that's the each y value. But I want everything in terms of x, so let's go ahead and solve this y value in terms of x. So y squared is equal to 4 minus x squared. From here I can say y is equal to square root of 4 minus x squared. It's actually plus and minus, so there's a top piece and a bottom piece for the y value. But I'm talking about the length of the side of the square, and length is never negative, so I'm going to keep the y as square root of 4 minus x squared. So side of square, this is my squared, side of the square is going to be, so here's the y value that I'm talking about. This y value is equal to square root of 4 minus x squared. This y value is also square root of 4 minus x squared, and that's where your origin is. Okay, so side of the square will be root 4 minus x squared plus root 4 minus x squared, which is 2 root 4 minus x squared. That is going to be the side of my square. Okay, so what is the area of the square? So area of one cross section is going to equal side squared. So I'm going to do 2 root 4 minus x squared, everything squared, 4 times 4 minus x squared. That is going to be my area of one cross section. How about volume of one cross section? Volume of one cross section. Okay, volume of one cross section would be the area of cross section times the width of cross section, which is delta x. And now if I want the volume of solid, then I'm going to integrate the little areas of the cross sections that I have. Volume of solid, so it is going to be 4 minus x squared dx. The delta x becomes dx operator, and now we need to integrate over the regions where cross sections are, and the cross sections start at -2, they end at +2. So -2 to +2, that's where the cross sections are. And go ahead and integrate this. Take a minute, go ahead and evaluate this definite integral and come back and check your answer with me. It's going to come out to be 128 divided by 3. Okay, that was example 1, volume of a solid whose cross sections area is known. Okay, next example. Cross sections are equilateral triangles perpendicular to x-axis. Okay, so here's a picture showing equilateral triangles perpendicular to x-axis. So we're going to start with really small triangles here, and triangles are getting bigger and bigger. When we get to the middle, we have our biggest triangle, and then they start getting smaller again. It is a part B to the same problem. Your base is still the same solid circular base of radius 2. Okay, so we see here we have an equilateral triangle. That means all 3 sides are equal. In the previous problem, we did find out that this is the y value, which was equal to y is equal to square root of 4 minus x squared. We did use the equation of the circle to get here. So this little piece is the y value, and side of triangle is actually going to be, the side of triangle would be twice of it, so it's 2 square root of 4 minus x squared. Okay, and now we want to find out the height for this triangle. So how can we find the height for this triangle? There's multiple ways of doing this. We can find the height of the triangle in multiple ways. We can use 30, 60, 90 triangle, or we can go ahead and use Pythagorean theorem. Okay, I'm going to use Pythagorean theorem, but you can also use 30, 60, 90 triangle. They both would work out. So this little piece, I'm just drawing this much of the triangle. Okay, I want to find the height. Okay, I know the y value I have is, the one on the bottom is square root of 4 minus x squared, and the side over here, this is a side of equilateral triangle, that would be 2 times square root of 4 minus x squared. Okay, so we know from Pythagorean theorem, leg squared plus leg squared equal to hypotenuse squared. So from here, we can do leg squared plus leg squared equal to hypotenuse squared. So hypotenuse squared is equal to leg squared plus leg squared. So this turns out to be 4 times 4 minus x squared is equal to h squared plus 4 minus x squared. All right, subtract 4 minus x squared from both sides. 4 times 4 minus x squared minus 4 minus x squared. That turns out to be 3 times 4 minus x squared. 3 times 4 minus x squared is equal to h squared. And then from here, we can say h turns out to be the height of the triangle, turns out to be 4 minus, let's see, yeah, like squared 4, that's a 3, h squared would be, yeah. Okay, so that would be square root of 3 times square root of 4 minus x squared. That's what the height would turn out to be. Okay, square root of 3, 4 minus square root of 4 minus x squared. Right, when we do the square root, 4 minus x squared. Square root and square cancels here. All right, so if I want to find out the area of triangle, it would be 1/2 the base times the height. Let's look at area of one triangle. It would be 1/2 the base times the height. 1/2 the base of one triangle. We just know that is the whole full side of the triangle. Base of one triangle would be 2 square root of 4 minus x squared times the height would be square root of 3 times square root of 4 minus x squared. Let's see, what can I cancel over here? The 2 and 2 can be gone. I'm still left with square root of 3, but these two square roots, when they multiply, I'm just left with 4 minus x squared. So that is my area of one slice, area of one slice. So this is area of one slice. What's going to be the volume of one slice? So volume of one slice, or volume of one cross section, that is going to be the area times delta x, because the cross sections are perpendicular to x-axis. How about the volume of solid? All right, so for volume of the whole solid, we need to look at where do the cross sections start. They are from -2 to +2, and then square root of 3 times 4 minus x squared dx. Delta x becomes the operator dx. Again, this evaluation, definite integral, go ahead and take a minute to evaluate the definite integral. It is going to come out to be 32 root 3 divided by 3. Okay, and that's the area of the solid whose base is a circular shape with the radius 2, and the cross sections are equilateral triangles perpendicular to x-axis. All right, moving on to the next example. Find the volume of a solid if the base is bounded by y equal to x squared and y equals 4. Okay, let's draw the base really quick. How does the base look like? Y equal to x squared. Okay, that's a parabola. And y equal to 4. So, okay, so this is my base. This is the base of the solid. Okay. All right, so part A, cross sections are squares parallel to x-axis. Okay, parallel to x-axis means they are perpendicular to the y-axis. All right, so I'm going to try to draw the cross sections again. I'm trying to draw a 3D shape in a 2D space. So try to imagine how it would look. This is how the cross sections are going to be. Okay, if cross sections are perpendicular to x-axis, y-axis, the width of cross section, width of each slice will be in terms of width of each cross section will be delta y. Okay, so my goal is to find the side of the square, because the only thing that would require some work from you is finding the area of the solid. To find the side of the square, how do we find the side of the square here? Okay, let's see. To find the side of the square, we need to figure, let's make it a little different color. We need to figure this little piece out. Looks like that is the x value. But we want to have this x value in terms of y, because this integral will be in terms of y, as the width of the cross section is delta y. Okay, so that's each x value. So if I write x in terms of y, I can say x equal to square root of y. So side of the square would be, so this is square root of y, and this piece is also square root of y. So it would be 2 root y. That's the side of my square. And then area of my squared, area of square would be area of square will be the square of the sides, which is 2 root y squared, and that's going to be 4y. Okay, how about volume of one cross section, volume of one slice? That is going to be 4y times delta y, which is the area times the width. That's the volume, 4y times delta y. How about the volume of the solid? Now, volume of the solid, once you know the volume of one cross section, it's not too much work. You only need to think about the limits of your integration. Those are wherever your cross sections start to wherever your cross sections end. Okay, so in this case, cross sections start at 0 and they end when y is 4. So 0 to 4, 4y dy. And that integration is not very difficult. It is just going to be 4y squared over 2. The bounds are 0 to 4, which would be 32. Okay, so just imagine it's a 3D shape. You have a really large square at the end, and then your squares are getting smaller and smaller, and you're going to have very small squares as you go towards the origin. Okay, good, awesome. Next problem. Actually, it's the same problem, different or separate part to it. So we're still dealing with the same base, but now cross sections are isosceles triangles with hypotenuse on the base. Okay, isosceles triangles with hypotenuse on the base. Let me go ahead and draw the shape. It's always nice to draw the shape first. Okay, let me draw the shape really quick. So we have the base is a parabola. Looks like this. Y equal to 4 over here. Cross sections are isosceles triangles, not equilateral triangles. Isosceles triangles, that they have two sides equal and one side that is not equal. Okay, cross sections are cross sections are isosceles triangles with hypotenuse on the base. So they are right isosceles triangles. Please add another. They are right isosceles triangle. Add another word here. Right isosceles triangles. They are not just isosceles triangles. They are right isosceles triangles. Okay. So back to the problem. In this case, the width of triangles would be in terms of delta y, because they're perpendicular to y-axis. So the width of triangle will be, also add the word parallel to x-axis. That is missing over here. Should say that. Okay, cross sections are isosceles right triangles with hypotenuse on the base, and cross sections are parallel to x-axis. Okay, width is delta y. We want everything in terms of y. Let's go ahead and think about our isosceles right triangle here. So this is isosceles right triangle. This is a 90 degrees angle here. So this would be 45 degrees and this would be 45 degrees. Okay, we can split it into another 45, 45, 90 triangle. Now, in the previous problem, we just found out that this is the x value, but we want it in terms of y, and it was square root of y, and this is also square root of y. So one side of triangle, or we can say hypotenuse of the triangle, not just one side, hypotenuse of the isosceles right triangles, hypotenuse is equal to 2 root y, because it's root y plus root y. It's 2 root y. Okay, so this is 2 root y. In a 45, 45, 90 triangle, if you recall the ratio of 45, 45, 90 triangle from the trig, there's multiple ways to find the sides from here, but I'm just gonna remind you about 45, 45, 90 triangle. If this side is x, this side is x, this side would be root 2 times x. Okay, so this would be root 2 times x. So again, if you think about the ratio, if this side is x, this side is x, this side would be root 2 times x. How much is x going to equal? In this case, x will be equal 2 over root 2 times square root of y. Okay, 2 over root 2 times square root of y, which you can rationalize if you want. And that's going to come out to be 2 root 2 root y divided by 2, which is root 2 times root y. So that's your one side, root 2 times root y. If you, that's your leg of the isosceles triangle, which is root 2y. You might wonder, why did I do all this? Because I'm trying to find the area of this triangle. Well, there's multiple ways. I could just do 1/2 base times height to find the area of the triangle. Yep, I could do 1/2 base times height. Again, so I'm going to use this as the base, this times this as the height for that triangle. Area of one isosceles right triangle, it's 1/2 base times the height, which is 1/2. The base is a leg, the height is a leg, root 2y times root 2y. So that turns out to be 1/2 times 2y, which is just y. So area of isosceles right triangle turns out to be just y. Now, let's go ahead and find the volume of the solid. I'm going to skip the step of finding volume of one cross section, because all I have to do is multiply the area with delta y. Volume of the solid, the entire solid, it is going to equal wherever the triangles start. They start at 0, they end at 4. So from 0 to 4, area of one cross section, which is y, width of one cross section, which is delta y, and that integral, I'm not going to solve it. You guys go ahead and evaluate that integral. It's y squared over 2 from 0 to 4. Go ahead and simplify. Okay, so simplify, evaluate the definite integral. All right, next example, cross sections are semicircles with diameters across the base. So here we have the same base still. Cross sections are still my parabola. Okay, cross sections are, in this case, cross sections are semicircles with diameter across the base. So let's see how does that look like. So this is how the cross sections look like in this case. Cross sections are semicircles with diameter across the base. Okay. So my goal is to find the area of one slice, area of one cross section, area of one cross section. It is going to be pi r squared divided by 2. What is the radius? If you look at it carefully, this is the radius, and we did find out earlier that the radius is square root of y. The width of slice would be in terms of delta y because the slices are perpendicular to the y-axis. Okay, so pi times the radius is square root of y squared divided by 2, which is pi y divided by 2. Okay, the volume of one cross section, will be equal to, from 0, the cross section for one cross section we don't need to integrate yet. We're just talking about one cross section. Would be pi y divided by 2 times delta y. And then we want volume of the solid. Volume of solid would be from 0 to 4 because that's where my cross sections are. They start at 0 and they go all the way up to 4. Pi y dy. I'm not going to simplify it. You guys go ahead and simplify, evaluate the integral. I'm not going to evaluate that integral. Okay. We're going to look at part D next. Cross sections are equilateral triangles with parallel to y-axis. Okay. Cross sections are equilateral triangles. In the previous one also it should say diameter parallel. The slices are parallel to x-axis. You should say with every problem. I think I missed typing it. All right, cross sections are equilateral triangles parallel to y-axis. So again, the same shape. Equilateral triangles parallel to y-axis would mean you have triangles that look like this, right? You have triangles that look like this. They're equilateral triangles. Okay, if they're parallel to y-axis, that means they're perpendicular to x-axis, and the width in this case would be delta x. Our whole integral needs to be in terms of delta x. So base of the triangle. Base of the triangle is actually going to be, if you think about this side, let's make it purple, a different color. How much is this side going to be? Well, from 0 all the way to here, it's 4, and then it's subtracting the y value from it. So from here to here, maybe it's easier if I draw. All of this is 4, and this little piece is my y value. If I subtract, then I have the side of the triangle. Okay, base of the triangle or the side of the triangle is going to be 4 minus the little y value. Y value comes from your curve, which is y is equal to x squared, and we do want it in terms of x. Okay, so 4 minus the y value, that will give me the base of my triangle, which is 4 minus x squared. Okay, so now we want to find the area of that triangle. Let's go ahead and split that triangle. It's an equilateral triangle, and I know this side is 4 minus x squared. Let's split it into 30, 60, 90 triangle. This is 60 degrees, this is 90 degrees, so I'm only going to focus on a 30, 60, 90 triangle. The triangle I did make it black just now. I'm only going to focus the 30, 60, 90 triangle. If you recall from trig, a 30, 60, 90 triangle, how are the sides related? For a 30, 60, 90 triangle, for a 30, 60, 90 triangle, the side opposite to 30 is the smallest. Hypotenuse is twice of that side, and the side opposite to 60 is root 3 times that side. Okay, so because I did draw the perpendicular bisector, I'm going to be dealing with just half of this 4 minus x squared divided by 2. And this would be 4 minus x squared. Okay, so the height, this side, using the ratio, comes out to be root 3 times 4 minus x squared divided by 2. So that would be the height of the triangle. That would make it finding the area of triangle easier. Area of triangle is equal to 1/2 base times height, which is 1/2. The base of triangle is 4 minus x squared. The height of triangle is root 3 divided by 2, 4 minus x squared. Okay, so it's root 3 over 4, 4 minus x squared squared. That's the area of one slice, area of one cross section, area of one triangle. Now we're going to find out the area of another, we're going to find volume of one slice, volume of one cross section. Okay, so volume of one cross section would be actually just the area of one cross section times delta x, and volume of solid. Now be very careful, where do the solids start, where do the solids end? That's going to be your bounds of integration, 4 minus x squared squared dx. Where do the solids start in this picture? So we need to think about what is the x value here, what is the x value over here, okay? Because those are going to be my bounds of integration. So how do we find those? We can find the points of intersection of y equal to x squared and y is equal to 4. So if you put x squared is equal to 4, you get x equals plus minus 2. So that tells you this is 2. I mean, not that is 2, but this is 2 and this is negative 2. Okay, so we have our bounds of integration from negative 2 to positive 2, root 3 over 4, 4 minus x squared, everything squared dx. And again, evaluate that integral. I'm going to leave that part for you guys. Okay, I'll cover a few more examples in the next video.